Alright, hello everyone. Welcome to Intelligence Maxing, day 81. So, I think for this stream, I have a quiz tomorrow for my computer architecture class, and kind of have no idea what I'm doing in class, so I'm going to spend maybe the next 2 hours going through some lecture notes, taking notes on that, but also trying some practice problems. And I think, just going off the top of my head, the past few things we've talked about so far was dynamic branch predicting. So when you have these branch instructions in your pipeline, what's the best way to go about that? I think one way is you can sort of unroll a loop. If it's a loop instruction, that branch just goes through multiple iterations. I think that's the biggest one. I think we also came across the idea of you have a branch history table. And so that's the idea of, I think you have these predictors, these predictor states, either not taken or taken, and you keep track of that. And then you also have this global correlation predictor, which is something that will alternate between weakly taken, weakly not taken, strongly taken, or strongly not taken, which I think is just something that's used in order to make a prediction about what instruction you want to fetch. So that's sort of the big high-level concepts. I think we also talked about this scoreboarding method, which relates to the idea of instruction scheduling. So usually with the pipelines we've been working on, it's been sequential instructions. You'll fetch, decode, execute, right back to memory, and then store it in a register. I think with a scoreboarding method, or maybe a dynamic instruction scheduling pipeline, you have, I think, 4 stages instead of the 5. The fetch, decode, that's in the issue stage. Then you have this idea of executing, and then memory right back. Or I guess right back and then memory. I keep confusing the two, so I'm gonna have to refresh on that. So that's kind of where we're at right now. I think this slide example goes over okay, so this is an example of the scoreboarding method. I think before we go through this, I do want to pull up another slideshow. Okay, let's see. There's one slide that I remember gives a brief intro on the new pipeline we're working with, so kind of want to see what that is. Now, here we go. Yeah, the dynamically scheduled pipelines. So they call it the scoreboard. A hardware technique that can do a good job of scheduling since it has perfect information about hazards. Basic idea is to start each instruction as early as possible, waiting for a table at a restaurant. That complete out of order. Okay, I actually like that a lot, because I guess when you're waiting for a table at a restaurant, I think you try to put the people that come in first at a table, but they could eat faster than someone that comes in at a later time, and so, or they take longer. So I think that's actually a pretty good analogy. And there's a lot to keep track of, and 2 main schemes to do bookkeeping. So scoreboard method, right? Okay, so in this 3 instructions, we have multiply, then add. It seems like we have a So it seems like, right after read, which is an anti-dependence. I think the true dependence is a raw. Right after read, or read after write, right? So instruction decode basic pipeline stage splits into two stages. Issue decode instructions, check for structural hazards, and right after write instructions. Read operands, wait until no data hazards, then floating point unit reads operands. Okay, so it distinguishes when instructions begin executing and when in between its execution. Okay. This one's a bit confusing. So distinguish when instruction begins execution and when it completes execution. In between, it is in execution. Okay, that's mouthful. All instructions pass through issue stage in order, but can stall or bypass each other in the second stage. Okay, so this is very important. I guess this is what it means, that they complete out of order, but they start in the same order, in order to prevent any of this control or data dependencies. So we get the right after read hazard when instructions execute out of order. Okay. Yeah, so this is the right after read hazard. Okay, to have multiple instructions and execute stage simultaneously, use multiple functional units or pipeline units or both, equivalent for purposes of pipeline control. Yeah, damn, this is a big ass computer, alright. So, what's a structural hazard? What is a structural hazard in computer architecture? Okay, when they need the same resource. So if you have two multiple instructions, they probably use the same logic unit, like a floating point ALU. That add.d can write to f1 before mult.d. If we allow add.d to continue. Okay, I see. Yeah, so that's that right after read. And then this will read something that is written by add.d. So I think this comment is just to show that if there's no data hazard, then this add instruction can just execute whatever and whenever. Okay, so with the scoreboarding, assume the processor has various functional units. Okay, in this case we have an integer arithmetic logical unit. For memory references, branches, or integer operations. Okay, we also have floating point multiply units, and then floating point add, and then floating point divide. Alright. I guess the scoreboard is kind of like the brain then of controlling each of these data buses to transfer data from the registers to the actual functional units. Okay, so I think there's a few things to keep track of then. The issue, read operand, execute stage. I might try to create some flashcards. I don't know if it's too little too late, but it's worth a shot. Oh, Allison, welcome to the stream. hope the meeting was okay. Alright. So let's... Yes. Alright, nice. What should I call this deck? Dynamic instruction scheduling. That's a mouthful, but I think it should be okay. Meow. Okay. That's a good way of describing this. guess these are the 4 stages here. The issue, read operand, execution complete, and then write result. Okay, and then these then are the different parameters we need to keep track of. Which I think is very similar to this unit. Okay. Okay, so this then is all of the functional units, and then you have a flag for the busyness. Track of which was okay. Okay, so in this initial state then, our scoreboard has 4 different functional units here. Okay, so maybe it would be nice to have a flashcard to describe. There's kind of like 2 segments to the scoreboard. First is understanding what operations are going through each functional unit, and the second is understanding, I think, what's stored in the register. Okay. 2 4 segments of a scoreboard. If a register expects an output, these are data points, what's actually stored inside the registers. Okay. So for the functional unit of segment of the scoreboard, what are the things should we need to keep track of? Okay, yeah, this is a pretty important question. So the first thing I think is whether the functional unit is busy. Call it B. I want to say also like a F, I, F, J. Register I, that is. I know we need the registers that are being read, and then the registers that are being written too. Also, my computer's about to die, so I gotta charge it real quick. Oh no, doesn't seem like there's a charger here though. But oh wait, I think there is. I just have to unplug something. There's like hella rust on some of these cables over here. It's kind of nasty. Yeah, oh well. Yeah, let's see. Okay. So, operation to perform. Number 3. Okay. So the register I. Name let's try to see this example then. And then that's probably it for this stream, so let's try to do that. Functional unit keeps track of the unit, the operation or the operand, the source registers, and then I think these are a flag to indicate whether or not the value of, let's say, fj is coming from another functional unit. So at the very beginning, we have 4 different functional units. 2 for multiply, 2 for add, and then we can see it's bifurcated, so we have our functional unit segment and then our register segment and then values for each register. So the first instruction we have, wait, what is S1? Instruction in stage, okay. Stage 1. So F0 is, we're adding this to F0. F2 is 3, F4 is 4, okay, and it does not depend on any it does not depend on any pipeline or any other functional unit. And I guess we'll make a note here in the register section that this value of F0 will be the output of whatever add1 is. So issue execute 1. So it's issue read operand execute right back, I think. Okay, so we have F6 and then F8 also doesn't depend on the output of anything. Okay, so it takes 2 cycles. So I think we'll need to do this 1 more cycle. And then F2 then depends on M1. Okay, so execute 2. So, well, 2, in this case, we have F0, which is the output of A1, and then we also, oh, I see, okay, so this down here is critical for our scoreboard, okay, and then F2, we look here, that's M1, alright, so we add that there, and this is the issue stage. Okay, so I'm assuming after this, so after 0, this is very beginning. So this is first clock cycle, second cycle, third cycle. Bless you. Okay, so second cycle, third cycle, and then fourth cycle here. Alright, okay, so fourth cycle here. We add 0. This doesn't become 7. Just to indicate it's ready. But this should be 7. so right after read hazard. No, sorry, read after write, because you're reading and then writing. Okay. So now it's 0, it doesn't depend on anything. This is cycle 4. Right. Okay, and then I guess it's finished. Alright. F4 then depends on A1, previously 0. Okay, so this instruction is still stalling, right? It can't move. A1, okay. Then we add instruction. So we're gonna have to stall here because we have a control hazard. There's no more units for us to use. This needs to finish. This needs to finish. Execute 1, 2, 3. Okay, so I think I need to go to 4, right? Stall. Okay, there's nothing that can happen. Okay, so I think this is going to be critical because what's going to happen then is this finish executing and go into the memory right back. So this then takes the output of 6 times 8, 48. We'll input that into this register here, F2. This will be set to 0. This will be set to 0. This will be set to 7. This will be set to 48. And then this will move on to the execute stage. So then this finishes at 2 ends. My mind is getting jumbled now. Okay, let me try to think. So add these two together, you get 14. This add 2. Okay, so that modifies. Does anything use A2? No. Alright. So A2 will be now 14. So it just gets replaced or clobbered. Gets the right back. So I think this instruction is still stalled. You just need to get right. Okay. Stalled as well. So we can see that. Yeah, because this is also reading from F0, so we can't write to F0 yet. because only one can go into the right, I guess, at the same time. Yeah, I think this is false. We just saw that happen. So you're still going to need to stall, right? Result, execution complete, read operands. Yeah, it seems like in this case they just skipped over completely the read operands part. Busy, yes, 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 yes. So this shows the dependency. Okay, so right now it's in the execution complete phase. So this will go to the write result phase. And then I think then each of these will have access to it. So RJ will be ready, and then RK will be ready. Okay, no. So you read the operands out, then you pass them in here. Okay, read after read is fine. Two clock cycles. So.e, where is it? Okay, so you have to insert the add instruction. Okay. Right after read, so this has to stall. Got it. Oh, man. Okay, so I think it's a good stopping point for the scoreboarding. Gonna end the stream here and then go work on some other projects. But Allison, thanks for tuning in. I appreciate the support. Go look at work. Hope the meeting went well. Alright. Catch you guys in the next one. Peace.